We are learning about probability. Under probability, we have some terms that are being used. We have the terms used under probability. Our first term is called sample space. By definition, sample space refers to all outcomes of a random experiment. I've said that sample space refers to all outcomes of a random experiment. Like for example, if you consider a coin tossed once, outcomes are we are having a head, and then tail. Meaning the sample space for a coin shall give us head and tail, giving us sample space as 2. Like in this case, a coin tossed once, we have the head and tail, and that's sample space. However, the expression for sample space when a coin is being tossed is given by the sample space for a coin is given by 2 to the power n. Why 2? We'll have 2 outcomes, that is a head and then a tail. This n stands for number of times of tossing that given coin. A coin tossed once means n equals to 1. When n is 1, I'll say sample space is given by 2 power 1, which will give us a 2. Meaning a coin tossed once, outcomes are head and tail, giving us 2 as our sample space. And then a coin tossed 2 times, it implies in this case our n becomes 2, giving us 2 to the power 2, giving us 4. In this case, outcomes would be, we have in here a head, we have in here a tail. We have in here a head, we have in here a tail. Meaning, outcomes would be, we have in head, we have in head tail, we have in tail head, we have in tail tail. In this case, we have in 4 outcomes. We have in outcomes would be, we have in head, we have in head tail, we have in tail head, and we have in tail tail. And likewise, a coin tossed thrice, it implies n becomes 3, giving us our sample space. In this case, as 2 to the power 3, giving us an 8. Now, if I consider, like say a die or a dice tossed once, outcomes would be we are having 1 up to 6. Meaning in this case, the sample space where a dice is tossed once are 1, we are having 2, we are having 3, 4, 5, and then 6. Meaning the expression for sample space dice is tossed once would be, it is 6 to the power n. Why is 6? We are having 6 outcomes. In this case, a dice tossed once, our n becomes 1, giving us 6 power 1, which becomes 6. A dice tossed twice implies n becomes 2, giving us 6 to the power 2, which will give us 36, and so on and so forth. And then our second term is called events. Let me use capital E to symbolize it. By definition, event refers to the desired outcome of a random experiment. Like for example, a coin tossed once, outcomes are head and then tail. When I tell you that find the probability of getting a head, in this case, the head is our desired outcome, meaning in this case, the event, the number of the events shall give us a 1. Why? Because getting a head is the required or desired outcome in this context here. Like for example, a die tossed once, outcomes are 1, 2, 3, 4, 5, and then 6. If I say find the probability of getting an even number, in this case, getting even numbers is our event. Meaning in this case, even numbers are 1, 2, and then 3. And therefore, the event would give us 3 in this case. And lastly, our last term is called probability itself. Probability refers to probability is given by the expression as number of events over number of sample space. If you divide the desired outcome over all outcomes of a given experiment to give us probability itself. Thus, probability is given by number of events over number of sample space. Let's have axioms or laws of probability. Like for example, if you have this and you have this Venn diagram, having this as A. In this case, if I call this A, this becomes a complement. Meaning, if I call this probability of A, this becomes probability of A complement. Meaning, if I add this plus this will give me a 1. Therefore, the probability of A plus probability of A complement, this will give us a 1. This one, take it this side, it becomes probability of A complement is given by 1 minus probability of A. In this case, for example, if I say the probability of A is equal to 0.2 and I say find probability of A complement, what you will do, you will say the probability of A complement shall become 1 minus the probability of A, which becomes 1 minus 0.2. This will give us a 0.8. Now this law works for intersection and works for union at the same time. Meaning, the probability of A union B, all of it complements. This one is same as Q, 1 minus probability of A union B. Likewise, this same rule works for intersection. Meaning, the probability of A intersection B, all of it complements. This will give us 1 minus P of A intersection B. This works for any symbol, whether it's M or B or anything. Meaning, if I say find probability of B complement, this still becomes 1 minus the probability of B. As simple as that. Secondly, all events which are real, like for example, this is our first law. Our second one, I can say 0 is less or equal to probability of a given number less or equal to 1. This simply means all events which occur naturally have 1 as their probability. The probability of John being a boy, it's 1. Then likewise, John being a girl, it is 0, it can't occur. However, probability is always between 0 and then 1. It can't go beyond 1 or below a 0. Then next, if you consider a Venn diagram of this kind, we have this and we have that. We have in two sets. There is set A and there is set B. This is probability of A. This one, probability of A of B. Now, of course, this one shall give us probability of A intersection B. This one is A only, meaning probability of A intersection B complement. This becomes P of A complement intersection B. Now, all of this one is A union B, which simply means that the probability of A union B is the same as this plus that. This one will give us P of A intersection B complement plus this one, probability of A intersection B plus this one, which is probability of A intersection complement intersection B. Now, from there, of course, I can say this will become like say star. If I consider this set alone, it implies this one, the probability of A intersection B complement plus the probability of A intersection B. These two added will give us probability of A. This one will give us probability of A. However, this one can go that specific side. I can have probability of A intersection B complement. This becomes probability of A minus probability of A intersection B. Meaning, if I say find this becomes probability of A minus the intersection. Now this one is a very important rule. If I use two symbols A and B, or P and Q, the probability of P intersection Q complements. This one we use the same rule. This becomes the probability of P minus probability of P intersection Q. Likewise, if I change them and I say find probability of P complement intersection Q, this one now becomes the probability of Q minus the intersection probability of P intersection Q. These are very important rules you must know under probability. They will be used often over and over again. However, my concern is only for this one. Now this one is same as this. If I replace this one here, it will give me the probability of A union B as this one is same as that. Probability of A minus probability of B intersection B, then plus, now come back here, we have the probability of A intersection B, and then minus plus probability of A complement intersection B. Of course, this one shall die with that one. When they die, I'll have probability of A union B as probability of A, this one. This is this plus this probability of A complement intersection B. The probability of A union B, this will give us probability of A plus. Likewise, this one can be simplified. This one, if I apply some technique like this, it will become probability of B minus probability of A intersection B. Now this one is called additive rule. Probability of A union B is same as P of A plus P of B minus their intersection. Now this works for any two events. If I use P and Q, the probability of P union Q is same as probability of P plus probability of Q minus the probability of P intersection Q. It's called additive rule. You've seen very well that for two events A and B, the probability of A union B, this simplifies to probability of A plus probability of B minus probability of A intersection B. This works for any two events, either A and B or M and L, and so on and so forth. However, let me explain something in regards to mutually exclusive events. Mutually exclusive events. Let me use a Venn diagram to show this one. If I have two events A and B, in this case, if A and B are mutually exclusive, these A and B have nothing in common. It implies we are having this as A, then this as B. This is probability of A, this is probability of B. These two are mutually exclusive, meaning the probability of A intersection B, this one becomes 0. That implies because it is 0, when I come back here, this is already 0. This part will vanish away. Therefore, for these two events, the probability of A union B, this becomes probability of A plus probability of B, then minus 0, which remains the way it is. So if I say events P and Q are mutually exclusive, it means the probability of P union Q, this becomes probability of P plus probability of Q minus 0, which remains the way it is here. Let me explain something in regards to independent events. If I consider events A and B, events A and B are said to be independent, whereby the occurrence of one can affect the other one. Like for example, two events A and B are independent. If the occurrence of A can't affect B, this simply means the probability of A intersection B is same as the product of the two independent probabilities. Meaning the P of A intersection B, this becomes probability of A times probability of B, which simply means the probability of A union B becomes probability of A plus probability of B minus intersection, which becomes probability of A times probability of B. If I consider two events P and Q, if I say P and Q are independent, it implies the occurrence of P can't affect Q, which simply means probability of P intersection Q. This becomes probability of P times probability of Q, and therefore their union will become probability of P union Q as P of P plus P of Q minus their intersection, which becomes now this one as probability of P times probability of Q. As simple as that. Let us see the Morgan's rule. Now this rule works for both intersection and union. If I consider two events A and B, the probability of A complement union B complement. Now this one becomes probability of A intersection B all of it complement, of which we saw very well that this one simplifies to 1 minus probability of A intersection B. If I take two events P and Q, the probability of P complement union Q complement, this will give us probability of P intersection Q all of it complement, which becomes 1 minus probability of P intersection Q. Meaning if you're seeing a union here, this becomes an intersection. This one is our demorgan's rule. And secondly, our second one, if I say now, if I change this symbol and I say probability of A complement intersection B complement. Now this was a union to give us intersection. This will give us a union. This will become 1 minus probability of A union B all of it complement. Sorry, like that. Meaning for two events P and Q, the probability of P complement intersection Q complement, this becomes probability of P union Q all of it complement, which simplifies to 1 minus probability of P union Q. And then lastly, let us look at our last one, that is this one. If I consider two events, that is A and B, events A and B, the probability of A occurring given B already occurs is expressed as probability of A occurring given B has already occurred. This one is expressed as, or simplified as, probability of A intersection B over probability of B. Meaning, if I consider the events P and Q, the probability of P occurring given Q has already occurred. Now this one shall become the probability of P intersection Q over probability of Q. In summary, we said at the beginning that number one, that zero for an event A, 0 is less or equal to probability of A less or equal to 1 as our first law of probability. Then we saw very well that for event A still, the probability of A plus probability of A complement, this gives us a 1. Then is our second one. Then we saw very well that for two events A and B, the probability of A complement intersection B, this one becomes probability of B minus probability of A intersection B. And then we saw very well as well, additive rule, that the probability of A union B, this becomes probability of A plus probability of B minus probability of A intersection B. And then number 5, we saw very well that if two events are A and B are mutually exclusive, it would imply the probability of A intersection B, this becomes 0, which simply means that the probability of A union B, this becomes probability of A plus probability of B minus 0. And then number 6, we saw independent events. If A and B are independent, it means probability of A intersection B, this becomes probability of A times probability of B. And then next, number 7, we saw what we call the demorgan's rule, the two of them, the probability of A complement union B complement, this becomes probability of A intersection B complements, which becomes 1 minus probability of A intersection B. And then our number 2, if I use intersection, the probability of A complement intersection B complement, this becomes probability of A union B, all of it complements, which becomes 1 minus probability of A union B. And then lastly, we saw for two events A and B, the probability of A occurring given B has already occurred, this becomes probability of A intersection B over the probability